Exercise 5.4. This is the last exercise due for this week, and it is Q2. And again, I'm doing the odd numbered problems since the even numbered problems are assigned for homework. Q, sorry, 5.4 adds two new rules, the biconditional rules. All right, so remember, again, each of the operators has an introduction rule and elimination rule. The introduction rule introduces that operator in the conclusion. So conjunction, introduction introduces a conjunction. Disjunction, introduction introduces disjunction. Conditional introduction, etc. Elimination rules get rid of. So you'll see the conjunction in the premise, and then it disappears in the conclusion. The disjunction in the premise disappears. The conditional in the premise disappears, okay? So same now with biconditional. Now again, I'm using this less than, greater than arrows consecutive to do the biconditional, which is the three, written with the 3 lines in the book, okay? So the 3 lines, the equal sign with the extra line, that's equivalent to this, this kind of diamond-shaped figure. Because again, these are on the keyboard, so you can use these in your homeworks as well. Alright, so the biconditional, the introduction rule for the biconditional, that again, introduction rule gives that to you as a conclusion. It takes 2 conditionals to make a biconditional. And not just any 2 conditionals. Notice the first conditional, if P then Q, the second one, if Q then P. In other words, the 2 conditionals have to be related, where the antecedent of one is the consequent of the other, and the consequent of one is the antecedent of the other. In other words, the order gets flipped. Here P is first, Q is second. Here Q is second, P is first. Or, sorry, I said that the wrong way around. But you get the idea. So P then Q, Q then P, together those make a biconditional. And again, that's why it's called a biconditional. It's the conjunction of 2 conditionals. Okay. Now the biconditional elimination rule is in some ways similar to the conditional elimination rule. If you have P biconditional Q and you also have either side of the biconditional, you can know the other side of the biconditional is true. And again, if you remember the biconditional truth table, that makes sense. The biconditional truth table comes out true only if both have the same value, namely if they're both true or both false. So if I know this biconditional is true, the whole thing, and I know that the first part is true, then the second part has to be true. Right? Or if I know the biconditional is true and the second part is true, the first part has to be true. And notice that's the big difference from the conditional elimination. Conditional only goes one way. P conditional Q, P gives you Q. It doesn't go P conditional Q, Q gives you P. That's not a valid inference. But biconditional, since it goes both ways, it's true if both are true. You can infer the truth of one part of the biconditional from the truth of the other. Okay, so let's go ahead and do some of the problems and see how the biconditional rule applies. All right. Now here we have our conclusion is a conjunction of 2 conditionals. All right. Now, last exercise 5.3, we talked about this conditional introduction rule. And we only used it when our conclusion was a conditional. But it doesn't have to be only when your conclusion is a conditional. You can use it to derive any conditional. So we'll see how to do that here, okay? So first we'll get this conditional. If I, then B. So how do we do that? Again, we indent, remember? Vertical line, assume the antecedent, and want the consequent. Assume I, want B. Then we treat that like a premise that we keep indenting. So we have I here. We can now apply the conditional elimination rule on 1 and 2. So line 1 is a conditional. Line 2 is the antecedent, so we can get the consequent. And now we can get B by itself by the conjunction elimination rule on 3. B is what we wanted. Remember, the want B is just a note to yourself. It's not doing anything else, but it does tell us what we wanted. So now we can get I conditional B by conditional introduction 2 through 4. So remember, this is a subderivation, so the conditional introduction rule is always going to be hyphenated. The first number 2 is where we made our assumption. The second number 4 is where we got what we wanted. So the whole subderivation proves the conditional. Okay, but we're not done yet. Now we need to get this other conditional. So we can do now another conditional introduction. Same way, we indent, we assume the antecedent of the conditional we're trying to get. We want the consequent. And we proceed the same way. Get B and J by conditional elimination of 1 and 6. Oops. Then we get J by conjunction elimination of 7. And since J was what we wanted, we're done with that. We go I conditional J by conditional introduction 6 through 8. Okay, so 6 we made our assumption, that's the first number. 8 we got what we wanted, J, so that's the second number. And now this goes, remember the conditional itself always goes back to the original scope line because that's been proven. Right? We know if I then B. That's what this showed us, that if we assume I is true, we can also show B is true. So if I, then B. This has been proven by this. Now this has been proven by this. We're still not done though, because our conclusion is a conjunction. So our last step is to make that conjunction. We're using the conjunction introduction rule. First conjunct is on line 5. Second is on line 9. Now we're done. Now we have the conclusion. So this is called multiple subderivations. Okay, because again, you can use conditional introduction not just to get the entire conclusion, but even if you want to get a part of a conclusion. So we used one conditional introduction to get this part. We used another conditional introduction then to get this part. And then we used a conjunction introduction to put them together to get our conclusion. Okay? That's possible. Now, one thing to be careful of is once you finish a subderivation, right? Like once we finished this and went back over to here, this is now all off limits. You cannot use it. And that's in fact why we had to assume I again. Right? We can't use this. Why? Because this was based on an assumption, I. We don't know if I was true. And everything in this subderivation was based on that assumption. So again, it's like quarantine, right? If it's based on an assumption you don't know is true, it's all sketchy. And so we can't use it again. We can use this though because we proved this. This has been proven. So this is good. But everything inside that subderivation, once you're finished with it, is off limits. So that's why we had to do get B and J again down here, etc. All right. So remember that whenever you use multiple subderivations or multiple conditional introductions, once you close one off, in other words, once you prove that conditional and go back to the original scope line, everything in the subderivation is off limits. Can't be used down below. Okay, so let's go to number 3. Here we have a conditional that we're trying to prove, right? So we indent, we use conditional introduction. We'll put the vertical line. We assume the antecedent, and we want the consequent. Okay, so now we'll get P by itself by conjunction elimination of 3. We'll get Q by itself, same way, conjunction elimination of 3. Now we can do 2 conditional eliminations. So let's do the first one. Oops. I'm gonna move this all down so I don't run out of space. So we got actually, wait. Sorry, this should be R. My mistake. So we simplify, or we get rid of the conjunction and get each of the conjuncts by themselves. So now we can get Q by conditional elimination of 1, 4. So 1 is a conditional, 4 is the antecedent, that gives us the consequent. Then we can get S by conditional elimination of 2 and 5. 2 is a conditional, 5 is the antecedent, that gives us consequent. Now we can put those together to get Q and S. Conjunction introduction of 6 and 7. That's what we wanted, so we're done. Come back to the original scope line, and we get that by conditional introduction of 3 through 8. So 3 was our assumption, 8 was where we got what we wanted, so that whole subderivation gave us that conditional. Okay, I'm getting a little short on time, so I'm going to go a little bit fast here. We're trying to get a biconditional. So again, remember the biconditional introduction rule? We need these two conditionals to get this biconditional. Right? So let me just go out here. So if we had K and J conditional A and B, and we also had A and B conditional K and J, right? Then according to the biconditional rule, right, if we have P then Q and Q then P, we can get that biconditional. So if we get P then Q and Q then P, we can get this biconditional. So in other words, we need to get two conditionals to get the biconditional. So let's start with this one. Again, these I'm just writing out here to show what we need. These aren't premises or anything, but they're conditional. So let's use conditional introduction. So K and J want A and B. We get K by conjunction elimination of 3. We get J by conjunction elimination of 3. Now we can use biconditional elimination with these. So we can get B by biconditional elimination 2, 4. 2 is a biconditional, 4 is one side, so that gives us the other side. We can do the same thing to get A by conditional elimination of 1 and 5. 1 is a biconditional, 5 is one side, so that gives us the other side. So now we can get A and B by conjunction introduction of 6 and 7. And that gives us K and J conditional A and B by conditional introduction of 3 through 8, right? So that's one of those conditionals, right? Now we need to get the other one. So we indent. I'm going to run out of time, so I'll do this quick. Assume A and B want K and J. Do the biconditional, do the same thing you did up here until you get, right, K and J. Then, 20, you get that conditional A and B, conditional K and J. So now you've got both conditionals, so you can get the biconditional. K and J, biconditional A and B, And that's biconditional introduction of 9 and